So we were discussing about linear algebra, in which we saw what do we mean by a rank of a matrix. What is this? Largest non-zero determinant. Non-zero determinant within the given matrix. And based on this definition, we established many useful results. That is, if A is a m cross n matrix, m greater than n, m less than n, what will be the maximum possible rank of A? We established. And if two rows are identical, what will happen? If two columns are identical, what will happen? These things and all we understood, and we established some results for rank of A. Second thing we understood was elementary operation. And what did we conclude? Rank of matrix is unaltered by elementary operation. So I can do some basic elementary operations like row. I can add two rows, or I can multiply one row with a constant and add with the other row, or I can multiply one column with a constant and add. All these basic elementary row operations are possible, and by this route I can find rank of a matrix very fastly. The goal will be, when we am doing an elementary operation, the technique here is to get more zeros. So if I get more zeros, I will get a reduced complex structure which can be solved very easily. So we have seen these things. Now let me introduce you to the notation of something called vectors. Okay? Vectors and vector spaces. Okay, this is very important. So we will understand what do we mean by vector and vector spaces. So vector here means it is a row or a column matrix to me. Okay, that's it. Please don't try to associate a physical meaning to a vector, like what you have seen, vector is a quantity having direction, magnitude, all those things. Don't try to assume that way in a physical sense. It is more of a logical understanding of the system. Why I am saying this is because if you can have a 3-dimensional vector, 5-dimensional vector, 7-dimensional vector, 100-dimensional vector also. The moment you start associating a physical meaning to it, it crosses 3 dimension. It is becoming very hard to visualize how a 4th-dimensional vector will look, how a 7th-dimensional vector will look. Okay. So with respect to this discussion, vector is either a row or a column matrix to me. That's it. The moment I say this, it can be even 100. So row matrix means how it will look. It will be one row. It can have m columns. Column matrix means how it will look. It will have one column and it can have some n number of rows, anything. So there can be how much ever big it can be. I can easily understand what is a vector is. Correct. So let us not limit ourselves to 3 dimensions. Okay. Now, first thing I want to understand is what are the basic operations possible. Basic operations in vectors. There are only 2 basic operations. One is called vector addition. Then the other one is called scalar multiplication. These are the 2 basic operations possible in the world of vectors. Vector addition means I have a vector called A. It can be a row vector or a column vector. I have another row or a column vector B. So I can add both of them. That is, this is a row vector, this is a row vector, this is a column vector. Or I cannot add a row vector. This is not allowed. Row vector cannot be added with a column vector. This is not allowed. Okay. I can add a row vector with a row vector or a column vector with a column vector of similar one. Means what? I can, even if it's A is a row vector, B is a row vector, If A is 1 cross 4 and B is 1 cross 5, then it is not possible. So A and B are of similar row vectors or of similar order, then I can do A plus B. So what? Let me say A as some A1, A2, so on till AN. And B as say B1, B2, so on till Bn. Then A plus B is nothing but A1 plus B1, A1 plus B1, A2 plus B2, A3 plus B3, so on till AN plus Bn. This is what is A plus B. This is called vector addition. So this is possible only when A is row and B is also row. A is column and B is also column. I cannot add a row and a column. And if this is having m entries and this is, say suppose A is having n entries and B is having some m entries, I cannot add it. Both should be having same number of entries, then only I can add it. Okay. Then scalar multiplication. Okay, what do I mean by scalar multiplication? I can, if A is a vector, then lambda is a constant or lambda is a scalar. Lambda is a scalar means lambda is a real number, some real constant. Okay, real constant means what? 1.2, 3.7, 1.9, minus 1.4. Like that, lambda is some real number. So lambda A is called scalar multiplication. Lambda A is called scalar multiplication. Means what? Suppose A is looking like this. A1, A2, so on till AN. Then lambda A will be nothing but lambda A1, lambda A2, so on till lambda AN. Clear? So lambda is a real number. This is nothing but scalar multiplication. So we were seeing about vector addition and scalar multiplication. Okay. Now what do I mean by scalar multiplication and vector addition? I should understand. This is very important. Okay, because these are the two operations possible in world of vectors. No other operation is possible. Okay, what do I mean by scalar multiplication? That is, I have a vector called A. A is a vector. Okay, I find lambda A. What does lambda A means? Lambda A is also another vector. So how does this lambda A will look? Lambda A is nothing but a scaled form of A. So for example, if I say vector A, I represent it like this. This is A vector. So what is scaled form of A? It can be a vector like this or it can be like this. One is, both will be like this. Let me call this as lambda 1A. Let me call this as lambda 2A. By scaling, what I mean, I either stretch or shrink the vector. The direction of vector is still the same. I am either shrinking the vector or stretching the vector. That is, if lambda is greater than, or to be very precise, determinant of lambda is greater than, or modulus of lambda is greater than 1, I am stretching it. If modulus of lambda is less than 1, I am shrinking the vector. Correct? I am either stretching or shrinking the vector. Correct? That's what it means. And if lambda is less than 0 means what? I am changing the direction of vector by 180 degrees. Correct? See, for example, if A is like this, if I multiply, if lambda is less than 0, say lambda equal to minus 1, then minus A, I will get minus A, which will look like this. I am changing the direction by 180 degree. And I can again change the direction by 180 degree and stretch it, or I can change the 180 degree and shrink it. Correct? So if lambda is less than 0, I am rotating the vector by 180 degree. See, by scalar multiplication, you should understand one thing. By scalar multiplication, I can rotate the vector by 180 degrees. Okay. So what does this mean? I can rotate either by, see here I am rotating, if lambda is greater than 0, I am rotating it by 0 degrees. Whatever is the angle of A, same is the angle of lambda to A, correct? I am rotating by 0 degrees. If lambda is less than 0, I am rotating by 180 degree. So in between angles are not, I cannot rotate by 90 degrees. So rotation by any other angle is not possible by scalar multiplication. Please remember this. I can either rotate it by 0 degree or by 180 degree. I cannot rotate it by say 87 degree or 95 degrees. These things are not possible. So this is very important. It is not possible to rotate by any other angle. By any other angle, it is not possible to rotate. Now what does vector addition means? I have a vector A, I have vector B, I am adding A plus B, I am creating a new vector in a new direction. That's what it means. Clear? This is what it means. Clear? So, with this as basics, we will proceed ahead and see why we are seeing all these things. See, I am doing something, there should be a meaning for it, right? We are doing all these things. What is the real meaning of this? So, meaning of vectors we will see. Now, let us take any system for example. In a physical sense, this is what it means. I have a system. This system can be anything. It's a physical system. It can be an electrical system, it can be an electronic system, it can be a mechanical system, it can be a biological system, it can be a share market, it can be anything. It's a system. Okay? I have an input, I have a output. This input is a vector, output is also a vector. The system is a matrix. The system is modeled as a matrix. So, what does this mean? I have an input vector called X. I have a system matrix called A. When I apply this input vector on this system, I get the output, say Y. So, I can write that Y is nothing but AX. Correct? Or I can say that A is a transformation matrix. The system transforms this input to another quantity which is the output. Say for example, I can relate this by numerous ways. Say for example, my system is a electrical system. Say for example, it is a electrical system. Say it is some motor or transformer or something like that. I apply a current, say it is a motor, I apply a current to the system which is a motor and I get a rotation. Correct? I apply the system is a motor, I apply a current, I get a rotation. Correct? Yes or no? So when the system converts the current variable to a mechanical, current is a variable X which is the input, it converts that to a motion, mechanical motion. Similarly, I can take the system for example as an electronic system. Correct? It is an amplifier. Say I apply X is a electrical signal. When I apply this, I get another electrical signal here, which is the amplified form of Y. So system A transforms this input signal to an output signal. Say let me say that it's a mechanical system. Mechanical system means what? A is say for example some pump or turbine or something like that. X is a input quantity. Say for example A is the turbine. I have modeled a turbine as A. the system turbine as A. X is a vector which tells me about the input. Say, let me say it is a steam turbine. Say X gives me the properties of the input qualities of steam. What is the enthalpy of the steam? What is the pressure of the steam? All those things. When I apply this enthalpy of steam as input to the turbine, I get so much mechanical energy on the shaft of the turbine. Where A is the system, Y is the output. Rotation, what I get from a turbine. Say for example, my system is a stock market, okay, where I know about the shares. So I say I take a decision of share. A is a system which describes my stock market. I take a input which describes my investment policies, share investment policies. I invest say 50 rupees in share company A share, 100 rupees in company B share, 150 rupees in company C share, like that. I have different companies, I am investing different amount of rupees, and I know what is the market condition prevailing. I can know what is the output, what will be the returns I will be getting from that investment in form of Y. Correct. So, the application of linear algebra is very wide. This is a very, very, very important understanding every engineer must have. This is why we are learning linear algebra. We should understand that intention very clearly. So I model the input as a vector, system as a matrix, I will get output as another vector. Clear? So we see that this vector analysis is a very powerful tool. I can model a multi-input, multi-output system in a very easy way. Clear? Now, having said that, let us examine what are all the meanings of this Ax equal to Y. What does that mean? Let me say A is a M cross N matrix. X, I am multiplying A with X, so X has to be N cross 1, and what will be Y? Y will be a M cross 1 matrix. So, when I say X is N cross 1, I say that by notation it is a matrix, column vector, or it can be a row vector. Don't worry about that. It's a real, all the entries here are real numbers of N entries are there. So I mathematically denote it as it is in the world of N. Matrix is contains all real numbers, and it is in M cross N world, so I denote it as RMN, and I denote this as RM. So what this happening, why I am now explaining the notation of a transformation matrix in terms of vector. So I have a system which is a M cross N matrix, to which I apply a N cross 1 input and I get a M cross 1. So what does that mean? This exists in a different world. These two worlds, if I say the vectors as a world, N cross 1 is a different world and M cross 1 is a different world. So these are different worlds. Correct? In the world of vectors, N cross 1 exists in the world called Rn, and N cross 1 exists in the world called Rm. Say for example, if this is if this is big complex or something, let us take an example. Let me say that my A is a 3 cross 2 matrix. This is my A. My X is 2 cross 1. My Y, how will be the Y? Y will be a 3 cross 1. 3 cross 1, all the 3 cross 1 vectors exist in the world of 3 dimension, correct? All 2 cross 1 vectors exist in the world of 2 dimension, correct? So, this world is different from this world, correct? Yes or no? A 2D world is definitely different from a 3D world. Okay, it might so be possible that I have a 2 cross 2 matrix. A is a 2 cross 2 matrix. X is 2 cross 1. Y is also 2. So, my X is also in 2-dimensional world. Y is also in 2-dimensional world. Correct? So, what does this mean? This may be same world or may be different world. The input and output may be in the same world, or the input and output may be in the different world. In terms of mathematics, this is what. In terms of a system, what does that mean? Input and output may be same quantities, may be related to same quantity, okay, same quantity or different quantities. What does this mean? Different quantities. What does this mean? Say for example, I take a motor as my system. What is the input to the motor? I give current. And what is the output? I get mechanical motion, correct? Mechanical motion. Correct? Let me take my system as a, for example, let me take the system as a transformer. In transformer what happens? I give current. The output is also a current. Correct? Yes or no? So, the input and output may be, see here current is the input, mechanical motion is the output. They are in different worlds. They are not in the same world. This is in the world of electricity. This is in the world of mechanical. Here I give current. This is also current. Both are in the same domain. This is also in the electrical domain. This is also in the electrical domain. Correct? Yes or no? So the input may be related to the same quantity or different quantity. That's what, in mathematical terms, that's what it says. The input may be in 2D, the output may be also in, the input may be in 2D, output may be in 2D, here 2D and 3D. And also, the number of the way the input and output are related is described by the system matrix A. So these are all very, very important points we should understand from this discussion. Now, having got that intuition, what does that mean? I have a system A input X, and I get an output Y. This is what I am going to talk in the rest of the session. Ax equal to y. What does that mean? So let us take for example, A is a system matrix. A, B, C, D. I have an input x1, x2. So what is y? Y is nothing but Ax1 plus Bx2. Correct? And what is this? It is nothing but Cx1 plus Dx2. Now, we will see the meaning of this. x1, x2 are vectors. x1, x2. See, x1, x2 is a vector. Correct? What is happening here? Ax1 plus Bx2, Cx1 plus Dx2. Correct? So, I can write this. How can I write this? Here, what did I observe from this? AC is a system vector. AC is a vector within system A. BD is a vector within system A. Correct? These are two vectors within system A. The system is comprised of these two vectors, if I talk that way. The output is nothing but AC times x1 plus BD times x2. Correct? This is what is happening. Correct? Yes or no? That is what is the output, right? Ax1 plus Bx2, Cx1 plus Dx2. So the output is nothing but the scale x1 and x2 are what? X1 and x2 are scalars. They are scalars. Let me write it clearly. They are scalars. What is AC? What is these two? They are the system vectors. Correct? The system itself is made of many vectors. Suppose if I write a system, the system itself is made up of many vectors like this. Correct? Can I say this? The system itself is made up of many vectors. Correct? Like this. Many vectors like this, and when I apply an input, each vector here in the system is getting scaled by the input and the results are getting added. So this is what I said in the world of vectors. only two operations are possible. That is scalar multiplication and vector addition. Only two operations are possible. That is scalar multiplication and vector addition. That is nothing but when I have a system, the system itself is comprised of many vectors like this. The system is a collection of vector. The other system is a collection of vector. Correct? This collection of vectors, when I apply an input, each vector is scaled by the input, and then the result is nothing but addition. That's what we saw here, right? When I have A, B, C, D, the system is comprised of A, C and B, D. Correct? And now I am applying a input vector x1, x2. Okay, what is the output? It is nothing but AX1 plus BX2, CX1 plus DX2. This is nothing but what? This is nothing but what? AC times x1 plus BD times x2. Correct? That's what I was telling you. AC is a system vector. AC is the system vector. BD is the system vector. They are scaled by x1 and x2. And what is the output? It is the vector addition of these scaled system vectors. So system output is nothing but what? Scaled addition of system vectors. I scale the system vectors, and what is the scaling factor? The scaling factor is given by the input. Correct? So the output of the system is nothing but, when I apply an input, the system vectors are getting scaled by the applied quantities, and then they are getting added up, and I will get the output of the system. This is what is the meaning of AX equal to Y. This is how any system in the world works. I can model any system in the world by this analogy. So it is a very, very powerful technique for analyzing any system in the world. Be it electrical, mechanical, physical, computer, any type of system, statistical systems, share market. The application of linear algebra is worldwide. The scope of linear algebra is very large. That's what I am trying to highlight here. Is this clear? Fine. Having said that, we started with AX equal to Y. Okay, this is where we started at. Okay, now we need to understand this AX equal to Y. What does that mean? So again I will write the same thing. A, B, C, D. I am taking an example. x1, x2, this is nothing but AX1 plus BX2, CX1 plus DX2. This is nothing but AC times x1 plus BD times x2. Okay? Fine. This is what we saw so far. So the system output is nothing but scaled version of system vectors, and the scaling quantities are the inputs of the system. Clear? Now I can have a system also like this. AX equal to 0. This is not a number 0. I will write it as theta, because theta is something like a collection of zeros. Okay, AX equal to theta or AX equal to Y. That means what? I have a system, I have a collection of inputs such that when I apply that collection of inputs, the system always gives me 0 as the output. Whatever, I have a collection of X such that any collection of that X I apply, it gives me only 0 as the output. Correct? So, what I can say, see for example, let me draw this. These are the collections of all possible inputs that can be applied to the system. This is the collection of all possible inputs to the system. Okay. Now, let me say that this collection, what I have shaded, is something special. If I pick any x, this is the collection of all the x that can be applied to the system. If I pick any x from this region, I am just drawing a diagrammatic representation. If I pick any x from region and apply it to the system, I always get 0 as the output. Correct? So, let me say that this is the collection of, this is y, collection of all possible outputs from the system. Now what does that mean? If I pick any x from here, I always land at only one point in y, that is theta. If I take any input from these regions, I apply, I get a different y. I get here, I get y1, I get y2, I get y3. These different y's I get. But if I pick any x from this region, I always get only 0 as the answer. Clear? This is what it means. That is, if I apply any x from this region, I will always get only one point in y, 0. If I apply any other x, I am getting different values of y. That is my observation. This is the first observation. So I need to know Ax equal to 0. This 0 is a matrix, okay, or I can call it as theta, and I need to know Ax equal to y. I need to analyze both. When this will happen and when this will happen, what do I mean by this and what do I mean by this, to study the system completely. Correct? So these are the 2 points which is in front of us, which we need to analyze. So what does Ax equal to 0 means? That is, I have non-zero, this is very important, non-zero x, but still I get 0 as output. I have a non-zero x. Means what? X1, if I go back to the example, I have A, B, C, D, X1, X2. This is nothing but giving me 0, 0. This is what we are discussing. Under what condition? X1, X2 not equal to 0. If x1 and x2 are zeros, definitely irrespective of the value of a, b, c, d, I will get 0, 0. Correct? So x1, x2 not equal to 0, I want to find what is a, b, c, d operated by x1, x2, I am getting 0. How it is possible? I want to know. Correct? How it is possible? That means AC times x1 is nothing but BD times x2. Correct? This is what I get as the output, and this is nothing but 0, 0. Means what? That is, it means AC times x1 is nothing but minus BD times x2. And most importantly, x1 not equal to 0, x2 not equal to 0. This is what is the conclusion we have. Okay. We will come back to the system Ax equal to y. Now let us proceed from here. What does this mean? What does this mean? We will come back to Ax equal to y little bit later. What does this mean? AC times x1 is equal to, means what? AC is nothing but minus x2 by x1 times BD. means what? The columns in A are dependent on one another. This is what we saw in the case of a elementary row operation itself, right? If I can reconstruct one column of A from other column of A, then what I can do, reconstruct this. See, what does this mean? AC is minus x2 by x1 times BD means what? I can reconstruct the row AC using BD. Correct? Where minus x2 by x1 will be some constant. So if I do some elementary column operation and cancel it, what will, see, okay, let us understand what does this mean. Now what does this mean? This means something like this. I have A, B, C, D. Okay. Now let me do a column transformation by elementary row operation, elementary column operation. Let me say that C2 is nothing but minus x2 by x1 times, one second, C1 is nothing but C1 minus C1 plus x2 by x1 times C2. If I do this operation, what will I get? I will get AC. A is nothing minus x2 by x1 times B I will get. Both are equal. So when I subtract, I will get 0, 0, B, D. Correct. So what will happen to rank of A? Rank of A is less than 2. Correct. That is A, if I say determinant A will be 0. Correct? Yes or no? Fine. So what we were discussing? We were discussing about the system AX equal to 0 and X is not 0. Correct? I have a non-zero X but still I get 0 as output. When this is possible? Say, if I take this as a 2 cross 2 system, I have x1, x2, this is equal to 0, 0, and from here we analyze that AC is equal to minus x2 by x1 times BD. Means what? BD. That is, I am able to reconstruct I am able to reconstruct this column using this column itself. This is, if I have, then in such a case we proved that determinant A will become 0. Correct? Correct. So, ultimately the conclusion is AX equal to theta will have a non-zero X as a solution. AX equal to theta will have non-zero X as a solution if and only if determinant A equal to 0. This is a very important conclusion. Else X equal to 0 will be the only solution to AX equal to 0. X equal to 0 is called the trivial solution of the system. What I am interested is the non-trivial solution. Non-trivial solution means what? Non-trivial solution is what I am interested to find. Non-trivial solution means what? AX equal to 0 and X not equal to 0. This is what is a non-trivial solution. That means if a non-trivial solution should exist, if non-trivial solution should exist, then what should happen? Determinant A should be equal to 0. This is called the consistency condition. Please remember this. This is very, very important. This is called the consistency condition. So, and the systems Ax equal to 0 are called homogeneous system of equations. Homogeneous system of equations. Clear? So for a homogeneous system of equation, if I have to find a non-trivial solution, the non-trivial solution will exist only when the determinant of the system matrix is 0. Clear?